Hello friends, I welcome you on BYJU'S Exam Prep, India's most comprehensive preparation platform for all the engineers. All the candidates who are joining me live, just quickly confirm your presence in the comment section and tell me whether my audio visual quality everything is clear so that we can start with the session. Till you are going to report me this, let me just brief you what is the ideal duration and what is the agenda for today's session. Friends, the ideal duration for today's session is going to be approximately 45 minutes, and the agenda of the today's session is that today we are going to practice some of the important problems on reactive power compensation. In one of our previous session, we have already completed the conceptual part of reactive power compensation, but there was a remaining portion. That remaining portion first we will discuss today in today's session. First we will discuss some conceptual theoretical leftover part in today's session, and then we will discuss the important questions related to compensation, or in general you can say reactive power compensation. So all the candidates who are joining me live, just quickly confirm your presence in the comment section, and do not forget to like, share and subscribe the session. Like the session, share it with your friends and colleagues, and subscribe to BYJU'S Exam Prep English YouTube channel so that you do not miss any of the important session, and do not forget to hit the bell icon. Very important. So let us proceed with the session. Some of you may be joining me for the first time, so there is a brief introduction about myself. My name is Ashutosh. As you can see on the screen, I have 11 plus years of teaching experience, completed MTech from IT BHU in 2010. I have written a couple of books on engineering ethics and power system, and my areas of expertise are power system, electrical machines, electromagnetic field theory, material science, and obviously engineering ethics. Is it clear, everybody? Shall we start? But before we start, a very proud statement I want to share with all of you. Once again, BYJU'S Exam Prep has got an exemplary result in GATE 2022 examination. We have got 41 aspirants under rank 50, 11 aspirants under rank 10, and 74 aspirants under rank 100. Some of the top rankers are Ram Balaji from Electronics AIR 1, Vandit Patel Electrical AIR 2, and Parvinder Singh Mechanical AIR 3. So what is the today's agenda for GATE 2023 power system? We are going to have some problem practice. Any of you who have attended my previous session on compensation, you must be aware that there was a remaining portion that we are going to discuss today itself, and then we will come to the problems. So if you are comfortable with this approach, you can say yes in the comment section. If you want me to directly go to the problems, then also no problem. I can switch to the problems directly also, because I have to act as per your wish. So just tell me quickly in the comment section what you want me to follow. You want me to discuss some conceptual part and then come to the problems, or directly come to the problem? So be quick in your answer and just tell me. And if you don't answer anything, I am going to take the decision. Yes, everyone? Just quickly tell me. Shall we go for the conceptual part first, or should we go for the problems directly? Any one of you? So I will wait for 10 more seconds, and if you don't answer, I am going to take the decision. Yes, everyone. Whenever you come to any YouTube session, make it a habit that you interact with the faculty. Okay. As a minimum gesture, you can say, hello sir, how are you, good evening, good morning, good afternoon. This is the basic minimum interaction you have to do. So no comments. So let me take a call. Let us start with the conceptual part first. I will not go into the depths, but I will give you some idea, some conceptual clarity which is required to solve the problems. In the previous session, we were talking about the compensation, and we have discussed that basically we have three types of compensation, reactive power compensation. The first one is static compensation. Then we have dynamic compensation. And then we have solid state devices compensation. Solid state devices compensation. If you remember well, we discussed that static compensation is going to be very fast, but it is not smooth. Why it is not smooth? Do you remember from the previous class? Because the compensation is available only in the multiples of the basic unit of compensation. I gave you one example also. If you don't remember it or understand it, you can watch my previous session on reactive power compensation concept 3, okay, 2 days back. Then dynamic compensation, we are saying it is not that fast. Why it is not that fast? Because in dynamic compensation we are using the synchronous motor. Now in case of static compensation, there is no rotatory motion is involved, there is no mechanical part, mechanical system is involved, so it is very fast. But in case of dynamic compensation, because you are using a mechanical system which must be having a mechanical inertia and mechanical time constant, and you know there must be some delay in processing the compensation required, so it is not that fast, but it is smooth. Why it is smooth? Because any value of compensation within the limits is available. Are you getting this? If you talk about the solid state devices compensation, in solid state devices compensation, basically we are using the power electronic devices. The best example is StatCon, static condenser. Static condenser. What is the full name? Static condenser. Okay, so this is going to be very fast because we are using the power electronic devices instead of the synchronous motor to provide the compensation. By varying the firing angle of the power electronic devices, especially the thyristor, you can have any compensation value that is required. So it is very fast also, and it is smooth also. If you want to see how this static condenser is going to look like, so you can understand it something like this. This is your line where compensation is required. Now this is your thyristor circuit which is required to control the reactive power being compensated, and this is your capacitor which is providing the compensation. So your static condenser or StatCon is going to look something like this. Is it clear, everybody? Just tell me in the comment section. Yes, good evening Neha, how are you? Sorry, Neetu. Good evening Neetu, welcome to the session. Everybody just tell me in the comment section. There is one more example, TCR. What is TCR? Thyristor controlled rectifier. Thyristor controlled rectifier. Okay. So in the last class we were talking about static compensation, so I am going to continue with the static compensation. In the static compensation, basically we have three types of compensation. The first one is shunt capacitor compensation, that we have already discussed. Then we have shunt reactor compensation, or simply shunt reactor, and then we have series capacitor. So we have already discussed about shunt capacitor. Now we are going to talk about shunt reactor and series capacitor a little bit. At least you can say yes or no in the comment section if you are able to follow me. If you don't interact with me and you are sitting idle in the session, so it gives me a kind of negative motivation. So I may not be able to give my 100% also, because I will be thinking, okay, students are not taking this class seriously, so why should I give my 100%? It is common human tendency, but if you interact, this is also a kind of motivation for me. So let us start with shunt reactor. Let us take the example. Suppose this is your generator, transmission line, this is your load, and this is the shunt reactor you have installed at the receiving end. Generator end voltage is Vs angle del, receiving end voltage is mod Vr angle 0 degree, take it as a reference. Transmission line is assumed to be lossless, so the resistance part is 0. The real and reactive power sent from the generating end is Ps plus jQs. The requirements of the load are P load plus jQ load, and suppose this is the shunt reactor. So if this shunt reactor is connected, what it is going to do? It is going to draw a current which is lagging this voltage by 90 degree. Yes or no? Because it is a pure inductor, pure reactor we are connecting. Suppose the current taken by the load is I, and this is the current in the line, that is Is. And suppose the power which is reaching the receiving end is PR plus jQR. So this is the complete case. Is it clear, everybody? Now let us see what are the important consequences of connecting a shunt reactor at the receiving end. What is the first thing going to happen? Can you guess? What is the first thing going to happen? There is going to be a voltage drop. There is going to be a voltage drop. Why this voltage drop is there? Because at the end of the day, what this reactor is doing? This reactor is going to absorb some lagging reactive power from the system. So what this shunt reactor is going to do? It is going to absorb some lagging reactive power from the system. So when the reactive power, lagging reactive power demand is going to be increased, definitely the voltage is going to be reduced. Voltage magnitude is going to be reduced. Is it clear? Now you can relate it with the formula. What is the formula? The voltage drop you can write as X. What is this X? This X is the reactance of the line, and this is Q shunt reactor divided by mod Vs. So this is the amount of voltage drop you are going to have if you know how much lagging reactive power is absorbed by the reactor. Is it clear? Now please try to understand. You are going to have a decrement in the power factor, and why you are getting a decrement in the power factor? You can just observe it from the phasor diagram. Suppose without shunt reactor, what is the situation? Without shunt reactor, what is the situation? This is, suppose, your receiving end voltage. This is your receiving end voltage, and some load is connected. That load is taking some lagging current. Suppose that current is something like this. Okay. And now you have connected a shunt reactor. Shunt reactor is also taking some current. Suppose that current is lagging this voltage by some degree. Now this current taken by the load and this current taken by the shunt reactor needs to be added so that you get the line current Is. Yes or no? So just add it up. So the final current you will be getting something like this. So this is going to be your Is, that is the line current. Now you can understand, sorry, I have discussed both the cases here. So if you see, previously the power factor angle was suppose phi 1, now it has become phi 2. So very easily you can write from this phasor diagram that phi 2 is going to be more than phi 1. So cos of phi 2 is going to be less than cos of phi 1. So you can say power factor in the second case is going to be less than the power factor for the first case. Power factor for the first case. Is it clear, everybody? Just tell me in the comment section. Good evening, Vagmi. How are you? Welcome to the session. Everybody just tell me in the comment section. Are you getting this or not? Now I'm going to give you a very important concept which is not generally found in various books of power system. That is what we are going to discuss. Something beyond books. When we say we are getting a decrement in the operating power factor, it is only valid for the lagging load condition. Lagging load condition. If you are having increment in the power factor, if you are having a leading load, then instead of decrement you are going to get the increment. This is extremely important, not generally found in various books of power system, and this is a beauty. Some people might be a little confused how connecting a inductor or the reactor will increase or improve the power factor. Actually it is not in general improve. There is a slight increase. If you want, you can prove it with respect to the phasor diagram. This is for the lagging load condition. Lagging load condition. Now let us talk about the leading load condition. If the load is leading, then what is going to happen? Suppose again this is your voltage. If the load is leading, so the current is going to be something like this. Suppose the load current is like this, and because you are connecting a shunt reactor, so that current is going to be IL. If you want to know the total current, add this current into this, so it is going to be something like this, and the final current will be like this. This is going to be your IS. So now if you observe, this was the previous power factor angle, and the new power factor angle is going to be like this. So for a leading load, you can say phi 2 is less than phi 1, or you can say cos phi 2 is going to be more than cos phi 1, or you can say power factor in the second case is going to be more than power factor in the first case. Everybody just tell me in the comment section, are you able to follow this? Good evening, Suman. How are you? Welcome to the session. So all the candidates who are joining me live, do not forget to comment whether you are able to follow me or not. We are discussing something really important. Is it clear, everybody? So now the big question arises. We are getting a voltage drop by connecting a shunt reactor. We are getting a voltage drop. We are getting a decrement in the power factor in general, because most of the time we are having the lagging load. In practical power system, hardly we get the leading load condition. Generally we get the lagging load condition. So this is going to be the general behavior for connecting a shunt reactor. You are getting a decrement in the power factor. So voltage is also reducing. Power factor is also getting reduced. So what is the advantage of connecting a shunt reactor? Why we are using it? Why we are using it? The answer is, basically we are using this shunt reactor to avoid over voltages in the system, or in general you can say shunt reactor is going to act as a Ferranti effect control device. Ferranti effect control device. You know what is Ferranti effect? No load or light load condition, the receiving end voltage magnitude becomes more than the sending end voltage magnitude. In order to avoid that situation, we are using shunt reactor. So shunt reactor basically we are using to protect the system against over voltages. Everybody just say yes or no in the comment section if you are able to follow this. Yes. If you don't say yes or no, How I'm going to know whether you are able to follow me or not? So this is all about the shunt reactor. Now let us talk about the series capacitor. Let us talk about the series capacitor. Series capacitor compensation. As the name indicates, you are going to connect the capacitor in the series. So the situation is something like this. This is your generator, this is your transmission line. Suppose this is the series capacitor you have added, and this is the load. This is the situation. Now the transmission line is going to be like this, JX. Suppose it is JX line, and this series capacitance is going to have minus JXC. You know, for the reactance, the capacitive reactance is going to be negative. You know that, yes or no? Yes, Mr. Gabriel Teshom. Okay. So if this is the generator, sending end voltage is Vs angle del, receiving end voltage is VR angle 0 degree, and load requirement is P load plus JQ load, and this is the real and reactive power sent from the sending end, and suppose this is the real and reactive power reaching to the receiving end. This is the complete story. Now what is happening here? Let us try to understand some basic fundamental concept here. When we were talking about the shunt capacitor or the shunt reactor, what is the first change that is going to happen in the system? Let us take the example of shunt reactor. The moment you connect this shunt reactor to the load end or the receiving end, what is the first change you are going to notice? What is the first change you are going to notice, my friend? The first change is that line current is altered. Line current is altered. Yes or no? The moment you connect it, it is going to draw some current. Yes or no? Any component, if you are going to connect to the system, it is going to draw some current. Yes or no? If you are connecting a capacitor, it is going to draw a leading current. If you are going to connect a reactor, it is going to draw a lagging current, but some current it is going to draw. So the first change that you are going to notice if you are going to connect a shunt capacitor or shunt reactor is the current in the line is going to be altered. I hope you are getting this. Tell me yes or no in the comment section. Are you able to follow this? Now let us talk about the series capacitor. Now what is the first change you are going to observe if you are going to put a series capacitor in place? What is the first change you are going to observe? Now please try to understand. Some people will say, no sir, line current is again going to be altered. No my friend, line current is not going to be altered. Why? Because if you take one bucket of water from the ocean, do you think the amount of water in the ocean is going to be changed? No. Shivam Bharadwaj, altered means changed. Altered means changed. Means change. Are you getting this? If you talk about the series capacitor, you can understand this, that the total reactance is going to be changed. Initially it was JX line, now it is JX line minus XC. So you must be thinking that yes, line current is also going to be changed, but it is not changing significantly. Why? Because if you take one bucket of water from the ocean, there is no significant change in the amount of water in the ocean. So the same logic, same theory you can apply here. So the first assumption that we are taking here is line current is not altered significantly. Second thing, even if you are connecting a series capacitor, capacitor is also always going to act as a source of lagging reactive power to the system, whether you connect it in the shunt or the series. So definitely there will be some voltage improvement. Definitely there will be some voltage improvement. That voltage improvement is voltage rise. Now this voltage rise, we have an approximate formula for this. So we are saying delta VSE is equal to IR XC sin phi R. This is the approximate expression for the amount of voltage rise in case of series capacitor compensation. Is it clear, everybody? Yes, Shubda, how are you? Welcome to the session. Good evening. Are you getting this? Now, by connecting this series capacitor, we have lot more consequences also. Let us try to understand. Another important consequence is fault level is reduced. System fault level is reduced. Now you will say, sir, why it is reduced? Let us understand with the help of the example. The first case, without series capacitor. Second case, with series capacitor. What is happening without series capacitor? Suppose this is your generator, this is the transmission line, and this is the fault. Suppose this is going to be JX line, okay, and this is the fault. So what is going to be fault current here? In the first case, suppose this voltage is going to be V here, or in general, suppose you are saying it is 1 per unit. Suppose in per unit, this is 1 per unit. So what is going to be the fault current here? It is 1 upon X line. In the second case, if you are going to use or add a series capacitor, the situation is going to be something like this. This is going to be minus JXC and this is JX line. And suppose again the generator terminal voltage is 1 per unit. So what is going to be here? The fault current is IF1 and here the fault current is IF2. So what is going to be this IF2? This is going to be 1 upon X line minus XC. So the total series reactance has been reduced. So you are saying the fault current is increased. Sorry, fault level is increased. Fault level is increased. Please take into account this. It is not reduced, it is increased. Fault level in the system is increased. Do you understand it? Why? Do you understand it? Good evening, Prakhar. How are you? Welcome to the session. Everybody just tell me in the comment section, are you able to follow this? Please change this. By mistake, I have written it reduce. It is increased. You can see it from here. The system fault level is going to be increased. Let us talk about the stability. How we are defining the stability? It is mod V1 mod V2 upon X sin del. Now see what is happening. This X is going to become X line minus XC. It means the total series reactance is reduced. If the total series reactance is reduced, this total value, which we are calling as P max, is the maximum real power received by the load. That is mod V1 mod V2 upon X. Now you are saying this X is reduced by adding the series capacitor. So this P max is increasing. Now if you are talking in terms of the constant voltage, constant power, constant real power supplied, Shivam Bharadwaj is saying, so sir, it's unbenefit. My friend, there is nothing, no word like unbenefit, but this is the disadvantage. If the system fault level is increasing, then this is the disadvantage. Okay, this is the disadvantage. Are you getting this? Let me just complete the concept, then you will understand why we are doing this. Now, for a given real power delivered to the load, if P max is increased, then definitely for a constant real power supplied, sin del has to be reduced, or you can say del has to reduced. Del reduced means what? Del reduced means what? If you see the approximate power angle curve, if this is del, if this is P, and if this is your sinusoidal curve like this, this is the del is equal to 90 P max condition. Suppose initially you are operating your system at del 1 and now you have reduced del because del is reducing. So now you are somewhere here, del 2. So by reducing the del, what is happening? The stability margin is going to be increased. And stability margin increasing means stability is going to be improved. So the basic fundamental application of series capacitor is what? The basic fundamental application of series capacitor is stability improvement device. So it is basically a stability improvement device. Is it clear, everybody? Just tell me in the comment section. Stability improvement device. Are you able to follow this? Just tell me in the comment section. Shivam, are you getting this? Shivam Bharadwaj, are you getting this, beta? Everybody in the session, just tell me, are you okay with that? Yes. Now, as we have said that the fault level or the fault current in the system is going to be increased by adding the series capacitor, there is one very dangerous situation which may happen in your system because of adding the series capacitor, and that is subsynchronous resonance. That is subsynchronous resonance. Subsynchronous resonance. In general, it is called as SSR. Now, this is one of the most dangerous situation in power system. Now, what is the basic idea about this subsynchronous? If you are exactly, Mr. Gabri Teshom is asking what is going to happen with the efficiency. Now, please try to understand very carefully. Whenever we talk about the efficiency or stability, we only talk in terms of the real power. You are adding the series capacitor, you are not tampering with the resistance part. So if the resistance is same, there will be hardly any significant change in the real power received. Are you getting that? So efficiency is not going to be that much affected. I hope you are getting that. Is it clear? Now, what is this condition, the most dangerous situation in our system, that is subsynchronous resonance? See what is happening. If you add the series capacitor and the rating of that series capacitor is so high that it gives rise to a resonance frequency to the line circuit, which is comparable with the frequency of mechanical oscillations of the system. Are you getting this? Have you heard that story? Whenever soldiers are going to cross a bridge, they are never going to use the same pattern of their footfall. The pattern of their footfall is different. Why? Because if the frequency of soldiers walking on the bridge matches or resonate with the frequency of oscillation of the bridge is going to collapse. This is what we say. Similar kind of situation you can understand in your system. If that circuit resonant frequency is going to matches with the frequency of mechanical oscillations in the system, there will be most dangerous situation in our system. This situation is so dangerous that there can be permanent damage to the shaft or the rotor of your generator. Now please understand, we are not talking about this much size generators, we are talking about this much size generators. We are generating power at a very high level. So this much big shaft or the rotor is going to be permanently damaged. You can assume the kind of dangerous situation that can be. Why we are calling it subsynchronous? Because that frequency is very low. Then synchronous frequency. Are you getting this? Everybody just tell me in the comment section. Is it clear? So this was all about the series capacitance. Now let me just talk about we have completed the static compensation part. Now let me talk about the dynamic compensation. Dynamic compensation, we have already discussed what is dynamic compensation. Let me just discuss some types of dynamic compensation. The first one is synchronous condenser. Second one is synchronous coil, and the third one is synchronous phase modifier. It is also called as phase advancer. It is also called as phase advancer. So let us first talk about the synchronous condenser. Synchronous condenser I am going to give you the most simple definition and understanding of Mr. Gabri Teshom. You tell me one thing. You tell me one thing. Real power is going to depend only on the resistance or not? Yes or no? Yes or no? What are the major losses because of the resistance part? I square R losses, copper losses. By connecting a series capacitor, are you changing the resistance? Are you getting this or not? Yes? You just brush up your concept of real power, reactive power, and you will understand this. See, there may be some minor variation, minor insignificant variation, but that is not because of the reason you are telling. That is because of the reason, because there is going to be some change in the voltage. Voltage rise is going to be there. Are you getting this? There will be some change in the line current. Because of that, there may be some change in the efficiency, you can say, but that is very insignificant, Baba. Please try to understand the difference between science and engineering. Science is about theory, engineering is about application. Where you apply in practical system. So science is about theory and engineering is about assumption. You tell me one rule, one law, one example in engineering where there is no assumption. You tell me one theory. You can join my personal Telegram channel. and whenever you get that situation, you can tell me. Engineering is all about practical understanding. Are you getting this or not? Is it clear? So what we were discussing, synchronous condenser. I am going to give you the most simple understanding of synchronous condenser. What is this? Only one line definition I am giving you. Synchronous condenser is an overexcited synchronous motor at no load. So two terms you have to underline: overexcited, no load. How we define synchronous condenser? An overexcited synchronous motor at no load. Are you getting this? This is your synchronous condenser. So if it is the overexcited condition, what is the condition? You can write mod EF cos del. This is going to be more than mod V, where EF is the excitation EMF of the generator, synchronous generator, del is the power angle, and V is the terminal voltage magnitude of the generator. Because of the overexcited condition, your synchronous condenser is going to behave as a source of lagging reactive power. Lagging reactive power. So when it is going to act as a source of lagging reactive power, definitely there will be some rise in the voltage and power factor is going to be improved. Whose power factor is going to be improved? The system's power factor is going to be improved. Is it clear, everybody? Shivam, if you I think you have missed the class. If you have, this is your doubt, or this is what you want to tell everyone? This is your doubt. I have discussed a very short logical trick how to decide whether it is going to be leading power factor or lagging power factor. I am just giving you a reference. If you are not comfortable with that, you can watch the previous session. There I have discussed in detail. See, this is actually a motor. What is the basic nature of motor? The basic nature of motor is to absorb power. This is the basic nature of motor. This is the trick I am telling you. What is the basic nature of motor? If I am a motor, I am going to absorb the power. But you are saying it is going to act as a source of lagging reactive power. If you are saying it is a source of lagging reactive power, it means you can say it is going to absorb leading reactive power. Yes. Source of lagging reactive power means load or sink of leading reactive power. Basic nature of motor is absorbing. So what is the operating power factor? It is leading. What is the operating power factor? Leading. Instead of going to that difficult phasor diagram, for which you might not be having time in the examination, you can use this trick. It is going to be 100% accurate. Is it clear, everybody? Just tell me in the comment section. Are you able to follow this? At least send me some emojis so that I am also motivated in this scorching heat. Okay, Shivam. So now let us talk about the synchronous coil. Synchronous coil is just the reverse of synchronous condenser. How we define it? It is an underexcited synchronous motor at no load. At no load. Underexcited and no load. Now because it is underexcited condition, so this is going to be mod EF cos del less than mod V, or you can say it is going to act as a sink of lagging reactive power. Sink of lagging reactive power. What is going to be the operating power factor? lagging because it is acting as a sink of lagging reactive power. शिवम भरद्वाज जी कह रहे हैं जो अभी आपने बताया वही कहना चाहता था. थैंक यू सो मच शिवम. So because there is an absorption of lagging reactive power, so definitely voltage drop is there and power factor is going to be in general reduced. Is it clear? Now if you try to understand properly, you can say that synchronous condenser is going to behave as if it is acting like a shunt capacitor. What is the major difference? Shunt capacitor is a static compensation device, whereas overexcited synchronous motor or synchronous condenser is acting as a dynamic compensation device. Your synchronous coil means inductor, it is going to act as a shunt reactor. Yes or no? Yes or no? The last part is synchronous phase modifier. Synchronous phase modifier. In general, it is called as SPM. Now, synchronous phase modifier, my friend, it is the most practical device for power factor improvement. Why I am saying this is the most practical device? Within no time you will just understand. How we define it? It is an overexcited synchronous motor having some real load connected to its shaft. What are the two important terms? Overexcited condition and some real load on its shaft. Yes or no? How it is going to look like? Suppose this is your load end, this is your load requirements, P load, JQ load, this is your synchronous phase modifier. What this synchronous phase modifier is doing? It is having some real load connected to its shaft. Some real load connected to its shaft. So because some practical load is connected, it is going to absorb real power from the system. But because it is overexcited, so actually it is going to supply the lagging reactive power to the system like this. That is QSPM. Is it clear, everybody? Just tell me in the comment section, are you able to follow this? If you want to have a comparative understanding of synchronous condenser, then you can understand this is synchronous phase modifier, and if you talk about the synchronous condenser, then it is going to look something like this. This is synchronous condenser. There is no load connected to the shaft. So there is no real power exchange, but because it is acting as a source of lagging reactive power, so it is going to supply, some lagging reactive power to the system. Is it clear, everybody? At least say yes or no in the comment section. Are you able to follow this? So this is all what we wanted to discuss in the conceptual part. If you have any query, then you can ask me. And now we are going to go for the questions. Shivam Bharadwaj is saying overexcited means leading power factor. No. Please understand. If you talk about the synchronous machine, there are three operating conditions. First one is overexcited. Second one is underexcited. And the third one is normal or level excited. You have to read something about the synchronous machine, synchronous generator or synchronous motor. No, we don't decide leading and lagging in terms of overexcited or underexcited. Please try to understand, otherwise you will be highly confused. Please try to follow the logic I am giving you. Listen very carefully. Whether it is synchronous generator, that is why I am writing synchronous machine. I am not writing synchronous generator or motor. This is going to be applicable for both of them. Overexcited condition you are going to define as mod EF cos del is greater than mod V. Underexcited condition you are going to define as mod EF cos del less than mod V. Normal or level excited, mod EF cos del is equal to mod V. If you go that way, you will be little confused. So please follow this approach. Whether it is generator or motor, if you are saying overexcited, so it is going to behave as a source of lagging reactive power. When it is underexcited, it is going to behave as a sink of lagging reactive power. Normal or level excited, neither source nor sink. Neither source nor sink. This is what we understand with respect to the overexcited, underexcited and normal or level excited condition for synchronous machine. Whether it is generator or motor, this is going to be true. Accordingly, you are going to get the different results. If you talk about the leading or lagging, please follow the approach I have given you. You will never be confused. Okay, is it clear? Any more questions? So that is a wrong question I have taken. It is about transmission line. We are much beyond the time, so I think we cannot take up the questions right now. 45 minutes is the allotted time. We are already much beyond time. So what I will do, let me just tell you, I will just share these questions in my personal Telegram channel that is available on BYJU'S Exam Prep. That is Electrical by Ashutosh Saxena. That is my name. And you keep on trying these questions. Okay, you will be getting the PPT or the PDF. Sink means load. Sink means load, absorbed. Source means generator. Okay, so these PPTs or the PDF, you will be getting the questions. That questions you can try on your own. Already we have discussed the conceptual part, so definitely you can give an attempt. And I'm not saying that we will not do the questions. Let me arrange one more session, one categorical separate session I'm going to plan someday in due course of time. In that session, we are only going to focus on the problems. Is it clear, everybody? So this is all from my side, friends. Thank you so much for joining me live in the discussion. Do not forget to join me tomorrow 8 PM on the same YouTube channel BYJU'S Exam Prep. I'm going to discuss some important questions for power system stability, for which conceptual part we have already discussed in the yesterday's session. Is it okay, friends? So thank you so much. Take care of yourself. All the best wishes. Stay connected. Thank you so much. Thank you everybody. Mr. Gabri Teshom, very interesting name. Shivam. Okay, let me see how many people are there. Shivam, Prakhar, Shubda, Suman, Vagmi, Neetu, everybody. Thank you so much for joining the session. It was a great time talking to all of you. All the best. Stay connected. Thank you so much. Thank you, all of you.